Looks like we can get started. Welcome back, everyone, and I appreciate you all making it in today. Like I mentioned before, this is probably one of the harder classes to attend right before getting into spring break. But also now that we're getting closer to a week-long break, this is a pretty great opportunity for us as well. We have 5 more weeks to get through after, well, let's see here. This is week 10, so 11, 12, 13, 14, 15, 6 more weeks really to get through after we come back from spring break. So this gives us a really great opportunity to get caught up if you're behind on any work and WebAssign. If you're behind on any of the quizzes, I'll also accept them for full credit as well. And if you have any questions while you're working over spring break, hopefully you don't have to work too hard, but I'll be checking my email every morning, so I'm still available for questions. We won't have any class or office hours, so it's kind of a catch-up week, relaxation week for us. With what we'll be doing today, we're finishing off section 4.2 on the last example, and we're making a start into the optimization section. We'll likely finish this when we come back on Tuesday after the break. So far, the new quiz number 8 is just going to be based off of the work we did in 4.2. Well, any questions or comments at all, folks, before we get started? Okay, let's jump back in then. So in section 4.2, we're looking into how the first derivative can help us find local minimums, local maximums. Then we went into issues of concavity. We found how the second derivative can help us to address when a curve is concave up versus concave down. And let's borrow this image right here. But just for a quick refresher before we jump into the next method, we say a curve is concave down, like in this region we see here, when it lies below all of its tangent lines, the tangent lines drawn in green there. Then we turn it around, say the curve is concave up, like in this region right here, if the curve lies above all of its tangent lines. Here the tangent lines are in blue, and the inflection point is when concavity changes. So when we go and turn this around into a method, here's what it looks like. Hang on, that's the increasing, here's the one we want. The concavity test, I think I put this here just for comparison's sake, but the concavity test tells us the curve is concave upward if the second derivative is positive. It's concave downward if the second derivative is negative. And the way we find intervals of concavity is then we take the first derivative of this function, compute the second derivative, took a little bit longer, but set it equal to 0 and solve. And then once we have the number line broken across these critical values here, we were able to divide up the curve to tell where it was concave down, a negative second derivative, versus concave up. Really, we just reproduced the same method we used in example 1. Only difference was now we set the second derivative to 0. It's not about increasing or decreasing, it was just about concavity. The inflection point is where it changed concavity, so we had 2 inflection points at -3 and +3. But concavity actually tells us a little bit more as well. That's what the next method down below is going to be all about. The so-called second derivative test can tell us where we have a local minimum and a local maximum. The second derivative being positive means it's concave up, but that leads to a local minimum, which we mentioned before on Tuesday. That's kind of confusing in a way. And likewise, the second derivative being negative means it's concave down, but that leads to the local maximum. And if the second derivative is 0 at the critical number, the test has failed in the sense that there could be a maximum or there could be a minimum or neither. There's 3 possibilities, and we have to look further to determine which of the 3. We would have to use the first derivative test to tell which one it is. Well, any questions at all, folks, with the concavity refresher or the brand new method here? Okay, well, here's a great way to think about the second derivative test and not get too mixed up. Here's our curve that we use to look into concavity once again. And this is what the second derivative test is telling us. If the second derivative is positive, that means we are definitely concave up in a certain region. But being concave up means, hang on, I'm getting a little mixed up. Oh, my colors are different. Hang on, that's not going to work, right? That's concave down, but I have that in green. But in green, I have the local minimum. My color coding's backwards. How about we get a new curve? That's going to be a little bit less distracting. I wasn't thinking of the colors when I grabbed this one. So how about another good curve would be this one before we put any marks on it. That'll help out a little bit better. Okay, these things are tricky enough without having the color coding being backwards. It already feels backwards enough in a certain sense. Let's start fresh with this curve right here. First thing we're going to look into when we're thinking about the new method, the second derivative test, is that f double prime positive means concave up. And likewise, the second derivative, f double prime negative or less than 0 means concave down. So now if we draw on our curve where we have a local maximum, that's going to be right here. So we have a local maximum at 2. Pointing to the y-axis, just as a reminder, the local maximum is the output value, the value on the vertical axis. Then likewise, we have a local minimum here at height 1. So that's our local minimum. And then if we do further analysis on this curve, we can find that, say, we place a horizontal tangent line here. That would mean there's a critical number. This is horizontal, meaning the derivative is 0. So f prime at 1 goes to 0. And that's the first part of the second derivative test. We're finding where the derivative goes to 0, the critical number. We have a 0 here, so that gives us that right information. And it's a local maximum, but also notice if we put more tangent lines here, like we had before, but in a different color, we can say here it's concave down in this region. Yet concave down leads to the local maximum. So it's just kind of unfortunate, right? That if you're looking into a local maximum, you have the second derivative negative, and those are kind of reverse directionalities. But this is right based on this picture. And likewise, if we look into this region right here, this is where we had the local minimum. If we put a horizontal tangent line, once again, we see that f prime at 2 goes to 0. So another critical number following that color coding. And then more tangent lines, just like on the last critical point, shows that in this region, it's concave up. I don't know exactly where the inflection point is, so I'll leave it kind of vague here in the middle. So concave up around this region. And where it's concave up, second derivative is positive, we're absolutely seeing the local minimum per this method here. So in an interesting way, concavity can lead to local minimums, local maximums. And so it gives us just another way to find these values. There's now 2 methods, the first derivative test to find them and the second derivative test. The only issue with the second derivative test is it can absolutely fail, and we'll see that happen on the next example. Well, any questions or comments at all, folks, looking into how this test works? Okay, let's put it to good use and see how it goes on the next example then. Next example is shorter than all of the rest of them in this set of notes. Here, the whole goal is to use specifically the second derivative test to find all local maximum values and all local minimum values. So here's the test duplicated again. I copied it with the color coding and I forgot to do that in the notes. So this has been redone just for the emphasis. And here's what the process would look like if we're using this test. Step one is we differentiate h prime of x with the goal of finding the critical numbers. So really at the parts that's highlighted in yellow, let's say for our step one, find all critical numbers for our given function. Our function's h this time. So let's go. Step one in finding the critical numbers is to just differentiate the function. So h prime is going to give us 15 x power 4 minus 15 x power 2. And that's the whole derivative. Last term is constant, so it goes to 0. Now, we want to simplify this as much as feasibly possible. And in the context of critical numbers, simplifying just means factor it as much as you can. So on our next step, we can say factor out greatest common factor, which is 15x squared, which is a form of division. Divide 15x squared here, and you'll get just x squared. Divide it here, and you'll get minus 1. And then this part factors. This is the difference of squares. So this becomes 15x squared times x plus 1 times x minus 1. So that's our first derivative in its most simplified form. The next thing we do to find critical numbers is solve h prime at x set to 0, which is really fast. We mentioned before in class, you can pretty much just read it off this line. Because it's now in its fully factored form, this set to 0 means 15x squared times x plus 1 times x minus 1 is 0. So we have 3 different things multiplying, resulting in 0. For real numbers, the only way that can ever happen is if 15x squared equals 0, or x plus 1 is 0, or the offender could have been x minus 1 is 0. So 3 different possibilities leads to 3 different critical numbers. Solution on this one is just 0. X being 0 solves that one incompletely. So let's list them out. We have critical number 0. From this one, it's -1. And from this equation, it's +1. These are the critical numbers of that function h. Once the critical numbers are done, we move on to the next step. The next step is really just get to the second derivative. When it says f double prime at c on both of these lines, what they mean is take the second derivative, plug the critical numbers inside that second derivative. Any questions at all, folks, before we go to that next step? Okay, here's our step 2 then. Let's put our second derivative test down here for reference as we go. In step 2, we take the second derivative now, h double prime at x. We could do it right here, but that's a product rule, right? It's an involved product rule with 3 different factors altogether. So the sensible thing is, when we say things are simplified, it depends on what you're doing. Here at the red dot, that's simplified for equation solving, but horrible for calculus. This is the one you want to use if you're differentiating, getting to the second derivative. That's the simplified form for purposes of differentiation. It's kind of tragic that the word simplify is so context sensitive. But differentiate that where the red dot is, and we'll get 60 x power 3 minus 30x. As a challenge, you can do it over here, but that's a product rule of 3 factors. It takes a lot of work to do it and simplify it down to here where it's done almost instantly. Once we have the second derivative, following the method where it says f double prime at c, it's just telling us take these critical numbers, plug them in. So next thing we're doing is computing h double prime. Let's just go down the list we produced. First do h double prime at 0. When we do the second derivative evaluate at 0, we're plugging it here and here. So that's going to be 60 times 0 cubed minus 30 times 0, and the whole thing is 0. Once we get an output, we make a conclusion right here on step 2. But this is not the world's best conclusion, right? It says the test has failed, specifically when it comes out as 0. Why did it fail? This whole test is based off concavity, like we were looking at with the explanation in the prior page. But when the second derivative is 0, it's neither concave up nor is it concave down. So we can't use concavity whatsoever to find a maximum or a minimum. If the instructions say use the test to find all local maximum and minimum values, then all we have to say here at this step is the test failed. Kind of a unsatisfying conclusion. But you wouldn't be asked to do anything further. We can just leave that as our conclusion. Our conclusion is we can draw no conclusion. That's kind of unsatisfactory. If we wanted to really investigate further, we'd have to now go to the first derivative test to see what can happen. It could be either a maximum, a minimum, or neither. Well, that's 1 down, 2 more to go. Any questions with the first conclusion? Okay, well, let's hope for a better conclusion on the next ones. Let's plug in -1. Second derivative at -1 means plug -1 into this function right here. That's going to give us 60, -1 cubed. That's just really a -60 minus 30 times -1. So it's -60 plus 30, coming out to a -30 altogether. So now that we have a -30, we're in this landscape. The second derivative came out negative. I don't know why I called it a landscape, but we're in this outcome right here. Second derivative is negative. That means we have a local maximum, but we need to find the local maximum and all local minimum values of that function h. So our work isn't done here, and -30 is not the local maximum. What we do next is we take that critical number -1, we plug it back in top to that original function to find the actual local maximum itself. So the next step looks like this. Because we had negative, we can say this implies h at -1, which is 3 times -1 power 5 minus 5 times -1 power 3 plus 4. This becomes a -3 rather, plus 5 plus 4 for a 6 altogether. Let me double check that. That's a negative times 3. That's going to be a -1 times 5, so positive 5, add 4. We get a value of 6, and that value of 6 is the local max. Let me reset my highlighting. I want to highlight mostly the outcome that we have a local maximum value at height 6 for this function. So that's 2 down, 1 less 1 to check. So we had kind of a more satisfying outcome on this one. Any questions on that conclusion? Okay, one more try. So last one is at +1. And kind of running out of space. Let me see if I can take a better screenshot here. Okay, that should do the job. So last one, we take h double prime at the final critical number. This time it's at 1. So we're just plugging 1 here. We're getting 60 times 1 cubed, so just 60, minus 30 times 1. So this is 60 minus 30, coming out as a positive 30. Now that we see that it's positive, we're in this particular outcome here, outcome number 1, positive second derivative means we can find a local minimum, but we actually have to find it. So we go to this next step. This will imply that h, returning back to the original function, this one, evaluate at the same critical number, 1, once again, notice how these match up together here. So now h at 1, but we're jumping back here, this is going to lead now to the local minimum. It becomes 3 times 1 power 5 minus 5 times 1 power 3 plus 4, but that's just 3 minus 5 plus 4, so 7 minus 5 for 2 is the local minimum. So we got positive here on the second derivative, but positive leads to a local minimum. Again, that always is kind of painful to have these directions feeling like they're reversing. And on this line, we had negative, but less than 0 for negative meant we have a local maximum. Naomi says, on the statements on the second derivative test, when it says f prime is equals 0, does that just mean one of the critical numbers has to be 0 in order for us to do this test? Yeah, essentially what's saying, once we're looking at this part, f prime is equals 0, we have to put all critical numbers inside this part right here. So really the method is first find all the critical numbers. Then once you have your list of every critical number, you plug them into the second derivative to see what outcomes you're going to get overall. So that's why we ran through all 3 of them at the same time. Only 2 of them, the last 2, actually gave an outcome of minimum versus maximum. The first one is where we had this outcome 3, the test failed. So as far as the other part of your question, once we find a critical number, the thing about the critical number is it will force the first derivative to go to 0, guaranteed by its nature being a critical number. There are other kinds where the derivative does not exist, but they didn't occur in this particular function. So it makes the first derivative 0, but a critical number could do anything whatsoever on the second derivative. So you'll always have that coming out as true. But when you put them back in the second derivative, it could be positive, it could be negative, or it could be 0 as well. Does that make sense with the question so far? Yeah, absolutely. Other questions or comments at the moment? Okay, well, let's take another look at this function because this outcome, once again, the test failed, is always kind of weird to run into. So we take the original function one more time, and now we're plotting it. We've got h of x is 3x power 5 minus 5x cubed plus 4. So here's our function. Desmos is already kind of highlighting the critical numbers there, but let's expand that a little bit more. Okay, so here's our original function. We have a horizontal tangent line here. That's the critical number -1. Another horizontal tangent line here at critical number 0. And one final horizontal tangent line here at critical number 1. Each time we say horizontal tangent line, we're essentially just saying the derivative at that value came out as 0 for slope 0 on the tangent line. And now when we look at our conclusions, we said that 6 is the local maximum. That's this one. We have a local max at 6. We said 2 is the local minimum, and that's this one. It goes from decreasing to increasing, giving the local minimum at height 2. But the concerning outcome is we said the test failed right at 0. Again, the test failing when the second derivative is 0 means anything could have happened. It could have been a maximum, minimum, or neither, but we couldn't detect it with this test. But if we use the first derivative test, here's what we would have found. The curve is decreasing until it gets to 0. It's at rest here. It's neither increasing nor decreasing. Then it's decreasing again when we move to the right of 0. That means at this one spot, it's a neither. It's not a minimum nor a maximum. But the first derivative test would have made that a certainty. Second derivative test, it has the major massive benefit of it's fast to use. We don't have to write down a number line. We don't have to solve an inequality like we did on examples 1 and 2. We just plug a number in and see if it's positive or negative. But then the second derivative test, it's fast on one hand, but then the other hand, it has a weak spot. It can fail, giving us a type of blind spot. First derivative test does not fail in this way. It's going to give you all the conclusions, and it will even tell you when things are neither a minimum or a net maximum. You'll see the first derivative is negative here, and it's negative here. So no local minimum maximum right at 0. Well, this is really just our first look at first derivative test and the second derivative test that we use down below. We're going to continue to use these in the next section in 4.4, optimization. Any last questions or comments, folks, before we go to that next section? Okay, so our whole work in 4.2 was to find local minimums, local maximums. But our goal in section 4.4 is a little bit bigger. We're actually going for absolute maximums, absolute minimums. And to find them, we're going to continue to use the second derivative test. We'll also use the first derivative test, but they've all been slightly tweaked. So here's the second derivative test again. It's only the two outcomes where we have a positive result. And it says, if the first derivative comes out of 0, and we have positive on that same critical number, it'll lead to a local minimum. But here's the tweaked part. If we further can say the second derivative is positive, not at the critical number, but if it's positive for all numbers x in the domain of the function, so that would imply that it's concave up in its entire domain. Here's a curve that's concave up on its entire domain, y equals x squared, for example. So if you have concave up and you found a critical number, then f at that critical number would be an absolute minimum, much like that's the absolute minimum for y equals x squared. And if you turn this around again and look into this one, here's the slightly differing statement. If the second derivative is instead negative, but not just negative on a critical number, we're extending beyond that because we want an absolute minimum. If you can show it's negative for all x in the domain, say this function, y equals negative x squared, for example, just flip the function around. If it's always negative, that would mean the curve is always concave up, and this one certainly is. Then at your critical number, you will have an absolute maximum, just like negative x squared has an absolute maximum right here at height 0. So here's the slightly tuned second derivative test, which leads to absolute extreme values. So now we're going for the absolute minimum and the absolute maximum. We didn't put outcome 3 when the test fails because we're saying it's either always positive, always negative. So we can't even use this test if the second derivative comes out as 0. It would exclude both of these possibilities at once, and the whole test is off the table. So this is going to be the next one we practice. We're also going to revise the first derivative test for finding absolute maximums and minimums, but we'll look into that when we get into the problem. And my example so far, if you're looking into the example 1, doesn't look like the most interesting problem in the world, really. It says the sum of two positive numbers is 15. What's the smallest possible value of their sum of cubes? I made this one have really, really minimum context because the purpose of example 1 is just starting to think about optimization. It's a fast problem. You possibly have already know what the result could be right away just looking at this. Or really just trying to highlight is how to use the method thinking about optimization. So as we go through the examples, the contexts are going to get more and more interesting. This one is rate of photosynthesis. Next one is something geometric, trying to minimize a cost. Final example is going to be something from pharmacokinetics, trying to find out when some kind of drug is going to have a maximum value in a bloodstream. And this one will be about blood alcohol concentration. Didn't quite make it in time for spring break. We'll finish this one after spring break. So starting off kind of gradually getting to those bigger context type problems, we'll begin with just a fast optimization. So it says sum of two positive numbers is 15 to start off. We want to know what is the smallest value of their sum of cubes. It says show all steps using second derivative test, and then state your conclusion using the context. I broke it down into two parts. And as far as the exam questions are going to be written, they'll be written in a similar kind of way, two different parts. We're using the second derivative test just so we can study. It's the first one we're introducing. But the first thing we really have to do is, if we're going to use this test, we need a function, right? It talks about a critical number of a function, a second derivative of that function being positive or negative. We can't do anything unless that function is on the table somewhere. So the first part A is just getting that function. We'll start here. This is a kind of constraint. We have two numbers, they're positive, and they sum to 15. So let's begin by saying, let x, y be two positive numbers for which it says the sum is 15. So we can just write down x plus y equals 15, and that gets us started. We definitely don't have a function here, and this is not anything we're trying to optimize either. This just is an ordinary linear equation. What we're trying to do is find the smallest possible value, meaning we're going for an absolute minimum this time, of sum of cubes. So we're cubing x, we're cubing y, adding them together, and we want to do the following. Minimize x cubed plus y cubed. So that's the thing we're trying to minimize altogether. So we have a constraint equation. X and y are only allowed to be positive, and they add up to 15, but we're minimizing this. It's still a challenge, right? This, well, you can think of as a function in two variables, but that's not what our functions are in calculus, not in this concept in calculus. We need a function of just one variable. So even though that's what we're minimizing right here, it's still not good enough. We need to knock out either the variable x or the variable y, your choice. Usually we'd get rid of y because we're used to seeing f of x. But if you did it backwards and got rid of x and wrote a function in terms of y, that would work just as well. Well, any suggestions on how we can get this into a function of just one variable? Where would you all start to make that happen? It's kind of a tricky question in a way, right? It's weird because there's two variables here on paper. However, the one tool we definitely have is that equation down there. Haley says plugging in 0 for x or y. Well, we could try that. Say if x is 0, y would have to be 15. But the trouble is that would give us just one potential sum of cubes. We'd have 0 cubed plus 15 cubed. But we're trying to make it as small as possible. So we'd have to keep updating, trying to make that smaller and smaller. That would be one valid way to find the absolute minimum. But it would be a tougher approach once the context gets a little bit more dicey, like in this one right here. It wouldn't be a very easy to apply that same kind of method. But still, if you're thinking of values for x and y, that's a great place to start. What we could do a little bit differently, instead of putting in a value for x or y, is just take this equation and solve it for one variable or the other. say if you solve this one for y, you would get that y equals 15 minus x. And then once we have that, it's kind of like your suggestion. Now we know a value for y in terms of x, and you can take that entire value, plug it in over here. So using y equals 15 minus x, we can say f of x is going to be x cubed plus y cubed. This still isn't quite right because we're saying this is a function of one variable x, but make that substitution right here. This becomes f of x equals x cubed plus, here's where y cubed was, but you can just throw this in, 15 minus x, by substitution. Now we've got a function. It represents a function of just one variable x, and so this calculus method up here is back on the table for us. We can't differentiate this one at all. That's differentiating using different techniques. But this one we can. It's the one variable function, just like we've been developing. Well, we've defined the function, and some problems it just gives us our function. We just jump immediately to the critical number. But on some problems, this is where all the fighting is. What is the thing we're minimizing in the very first place? Sometimes that's the heart of the whole question. And that's what was going on in example 1. Even though the context was short, it's a lot of work just to get to that step. But now we're basically redoing the last example of section 4.2. We've got a function, we're going to find its absolute minimum. The only difference is we're going for this new finely tuned second derivative test for the absolute minimum. Well, that means the next step in this process is find that critical number, but in doing so, that's what this is saying to do. This is what a critical number does. It takes the first derivative and sets it to 0, or solves when it's equal to 0 is another way to say it. So we should just differentiate this thing. So here's our next step. Take f prime at x. On the first term, it's not so bad, right? You just get 3 x squared. But then on the next term, it's a good review of the chain rule. And there are different things you could do. You could just expand that whole thing out and then differentiate that as normal. But I think actually hitting this with the chain rule, not just a good review problem, it's also just a little bit faster in my opinion. So we're going to minimize the algebra by focusing more on the calculus. Let's review how that goes. And this function here where we're differentiating, that's the inner function. And the power function to power 3, that's the outer function. So when we go to differentiate this whole thing, 15 minus x to power 3, first, you take the power 3, write it as a coefficient. The new power is 2. Chain on the next derivative, and plug into those two placeholders, 15 minus x. Now we're almost done with the first derivative. We just have to resolve what that comes out as. So we now have that f prime of x is 3x squared plus 3 times 15 minus x squared. And this derivative is not too bad. You get 0 here for the 15. Derivative of negative x is just a -1. And so now we're done with the derivative. The next step is, well, we're going to have to get that critical number. So the next step is simplify that as much as feasibly possible, which at least it kind of addresses why did we do these problems in chapter 3, where we took a lot of time simplifying some of the things down, where the algebra sometimes was more than the calculus. It was to kind of prepare us for this one and problems like it that are coming up later. So we're still just simplifying it. So on the next step, we can say it's 3x squared. I'm going to combine -1 with 3, multiply those together to get -3. Next, we can expand this out. 15 times 15 is 225. Then 15 times -x is -15 times x, but we get that twice when we FOIL. Then finally, go plus x times x, -x times -x rather, for positive x squared. So when we FOIL this out, we get all of those terms. Let's simplify the middle. The derivative is now 3x squared minus 3 times 225 minus 30x plus x squared. The algebra just kind of keeps going and going, but here's our next step. We can distribute the -3 into that group. The derivative of f at x is 3x squared. 3 times 225 is -675, then plus 90x minus 3x squared. And a nice little algebraic miracle occurs here. We've got like terms. The power 2 is just gone from this problem. So the first derivative of f at x, f prime at x, is now just a 90x minus 675. You know, honestly, thinking about this problem, if you did expand this, you're not using the chain rule, and that's a good chunk of algebra itself, but by not expanding that, we exchange the algebra from here by doing more algebra down here. So in any case, it's probably just about the same amount of work. At least we review to the chain rule. That's always good to brush up on. But any questions at all, folks, getting to that step down here? Okay, so the next step, really the same kind of stuff we were doing all the way back in section 4.1 with the closed interval method, the problem even before that. We did this a bunch in section 4.2. When it says find the critical number of f, this just means solve f prime at x equals 0. And that's why we took all the trouble of simplifying it down. We're doing the equation solving, so it's necessary. But it's linear now, so solving this, not so bad. F prime of x set to 0 just means 90x minus 675 is 0. And you can solve it by factoring and using the zero product rule, but here we probably do the normal thing. Add 675 to both sides. Then divide 90 into 675. This is where I'm going to definitely reach for a calculator at this point after fixing the penmanship. So 675 division by 90 gives us 7.5 exactly. So x equals 7.5, which probably feels suspicious. Again, this is one of those examples where you might have known the answer already if you've seen these kind of problems. When you say that two numbers are positive and they add up to 15, you're going to get the optimal absolute minimum when they're both half 15, 7.5. So if x is 7.5, y is 7.5 as well. But once we got to this step, again, we kept the context simple just to focus more on the method. We can say that this is the critical number of our function f, the one that we built ourselves. Once we have the critical number, the next thing to do is we're going to apply the second derivative test to that one and only one critical number. Well, any questions at all, folks? And this kind of a long slog through building the function and landing at 7.5. Okay, here's the next step then. Here's the second derivative test down below for reference. Once we have the first derivative, in order to go to the second derivative test, after getting the critical number, it's the 7.5 in this problem, solves f prime of x equals 0, we just take the second derivative. And we need to argue some way, somehow, that that second derivative is either always positive for trying to maximize or always negative if we're trying to minimize. We're actually not plugging anything into this function. That's if we're going for a local minimum, local maximum. We plug 7.5 into the second derivative. So this goes a little bit differently. We just take f double prime at x So that's this part right here of the second derivative test. But the second derivative is ultra fast now, right? It's just 90 this time. The second derivative of f at x is 90, and this is absolutely positive, right? It's positive for all x in the domain. X was just stated to be a positive number. So if the second derivative is 90, x doesn't apply. We can say that this is true for all x. It was a positive number, so it'd be in domain 0 to infinity. But once we have this part greater than 0, it means we have an absolute minimum. 7.5 wasn't the absolute minimum, so we have to look into the instructions to see exactly what we're doing. Sometimes these questions want the input value. They're being asked, at what input do you have an absolute minimum or maximum? But some questions want the output value. So we have to look into the wording carefully and see what they ask. It says, what is the smallest possible value of their sum of cubes? That means it wants the output altogether. Here's the function that we built. Now we know we're going to get an absolute minimum, but now we have to plug the critical number inside of it to get it. So we're at this part right here where the red dot is, finding the absolute minimum. But we're basically done at this stage. We can say, therefore makes it sound fancy. We did a lot of work, so that's justified. Let's go for a big therefore. The original function f at the critical number 7.5, we need to evaluate this, plugging it into those two spots. It'll be 7.5 cubed plus 15 minus 7.5 cubed, but that's really just 7.5 cubed again. This is just 2 times 7.5 cubed, really. Whatever that comes out as, that's the absolute minimum of the sum of cubes of these numbers. So one more calculator run. 2 times 7.5 power 3 gives us 843.75 exactly. And we'll say is the absolute minimum sum of cubes. So it's the absolute minimum sum of cubes because second derivative was always positive, which meant it's always concave up, so it had to have this kind of shape, a parabola-ish type shape opening downward, even though it's not a parabola. On this domain, it takes on that kind of shape. Let's double check that just to see what the geometry looks like in the background. If we put in this function that we built, f of x equals x cubed plus 15 minus x power 3, then we have to be mindful that the curve that we see, wherever it goes, it's way out there. Here's our curve. It's a lot more steeper than I realized. It's pretty steep, but oh no, can I control Z that? Yeah, thank goodness. But another thought is it had a domain, right? X was only positive values, so we would have to say 0 less than or equal to x. Well, that's not quite right. Positive means it can't be 0 either. So we have a domain on this, and we can surely make this look a little bit better. Let's say for the y-axis, we're going from 0 to, let's say, 15. That would give us a better view of the function. So this function that we were trying to optimize by finding an absolute minimum, it does have a particularly parabola-ish shape on this domain in this region. And right at 7.5, we hit that absolute minimum, 843.75. The shape where it's kind of bowl-shaped opening upwards also tells us it's purely concave up. Second derivative is positive in that region. But we did it, folks. We've optimized a sum of cubes. Our goal is to try to do this into more interesting and more applicable, realistic kind of real world scenarios in the next examples. So this one was kind of just our warm up. It was a tougher one because the algebra got kind of involved on it when we were doing the derivative, but mostly it's tough because this is a tough skill to build, just building the function itself. Any last questions or comments before we try out another one? Okay, well, here's our next thing to optimize. Here we're going to use the first derivative test. And one thing we'll resolve when we come back from the break is, why choose the second derivative test over the first derivative test? The idea is, how easy is it to compute the derivatives in the very first place? Notice in the last problem, the second derivative was really fast. We just got 90, really no steps to it at all. But for that function, the first derivative is a lot of work. The second derivative is a lot of work times 2. It's going to be a really tough chore to do the second derivative on that thing. And even after you've done that, the second derivative test is complicated in the sense that you have to show it's either always positive or always negative. And if you have a really complicated looking derivative, those are really hard inequalities to solve in the second place. So that means the second derivative, it only really works well if the second derivative is fast. And if you can show really quickly that it's either always positive or always negative, like in this example, it was just 90, absolutely always positive. But when the functions get a little bit more tricky, like this one, the second derivative test is torture on this. First derivative test, even though sometimes it feels like a lot more steps, is a lot nicer. We don't even have to take the second derivative. So that's what we're going to use on a function like this one for sure. We've done this first derivative test before. That was example 1 of the last section. But now it's tuned for absolute maximums and absolute minimums. It's pretty much the same statement, but what we're changing to get the absolute maximum minimum is we're going to say the derivative is greater than 0 for all x less than a critical number. So that means it's always increasing until it hits a critical number. And then it's always negative after that critical number c. So that it comes down. That means this critical number is unique. Exactly 1 critical number. Because if there was another critical number, it would have to turn around like this to give another horizontal tangent line, but then it would violate this when it said the first derivative is negative, decreasing for all x beyond that critical number. So if your critical number is at some value here, that means you have a horizontal tangent line, first derivative is negative. If it's greater than 0, or excuse me, it looks like I was looking at this one. Oh, no, we're on that one. If it's greater than 0, let me just highlight as we look at it. If it's greater than 0 for all x less than the critical number, so increasing, and then less than 0 for all x to the right of that critical number, so decreasing, you should have an absolute maximum for sure. And that's what we're seeing, an absolute maximum. So it's really the same first derivative test, but we're implying one unique critical number, which would say there was in fact an absolute maximum. And if you turn it all around and say the derivative is negative, that means it's going down, hits a critical number at c, meaning the derivative is 0 there, and then it goes positive, meaning now it's increasing, but increasing for all x beyond that critical number, never turning around again, then you're looking at an absolute minimum instead. So that's the logic of the first derivative test for absolute extreme values, absolute maximums or absolute minimums. Any questions about the procedure so far? Well, here's a pretty interesting context. It says the rate in milligrams of carbon per cubic meter per hour, so that's a complicated unit already, at which photosynthesis takes place. So these are the units of photosynthesis. This part, carbon per cubic meter, it's a rate. So we're also talking about per hour. So the rate at which photosynthesis takes place for a species of phytoplankton is modeled by this function. So P for photosynthesis, the rate at which it takes place, and I for light intensity. So you can imagine this is in maybe some kind of basement lab where they're looking into some species of phytoplankton. They're just seeing how much photosynthesis takes place. And you have to turn on the lights for them to engage in photosynthesis. So I is the light intensity. And it has an interesting unit as well. I'm always kind of amazed by the different units mankind has come up with. For light intensity, how bright the lights are turned on, this is measured in, this is a legitimate unit, thousands of foot candles being the unit of light intensity. I think I usually think of light intensity measured in lumens. If you're buying a flashlight in Walmart, for example, that's what they're going to be measured in. But that's a bona fide unit as well, so that's what we're going to go with. So we have some complicated lab setup where there's phytoplankton growing. You can adjust the light intensity in a continuous dial, and this is the rate of photosynthesis that adjusts according to how bright the lights are, I in light intensity. That already applies something about the domain of this function. If we say I is 0, that's absolute darkness. That means there should be no growth whatsoever. And that's true. If you plug 0 into this function, you have 0 divided by 4, it's 0. So your phytoplankton, they're just dying. That's kind of sad. No photosynthesis happening whatsoever. So this also implies the domain is going to be bracket 0 to infinity. 0 being the total darkness, and then positive values are going to be the possible light intensities. Yeah, absolutely, Haley. 0 is kind of a grim reality. They're not going to last too long, so that's a weird thing that they would do. We're going to hope that they keep the lights on something larger than 0, but that's our implied domain in this problem. You notice the context is kind of touchy on this one. We're really going to show that there's exactly one critical number. This was a humongous observation that essentially we're just saying light intensity I is greater than or equal to 0. So we need to really use that if we're coming up with exactly one critical number. So it now asks us the question, sounds like we're thinking of absolute maximum, the most photosynthesis production, and it asks us for what light intensity is P a maximum? And the wording is pretty interesting as well. The solution to this problem is not the output to the function, like in the prior problem. We plugged the critical number into the function and got the output. Here, our whole problem is done once we say at what input do we get the minimum. If you found the output, it wouldn't hurt. But if you're doing this as a WebAssign problem, they don't actually want the rate in a photosynthesis. They want the light intensity that leads to the maximum. They want I in 1,000-foot candles. So we're going to use a first derivative test. But in the process of that test, first thing we do is find the critical number of the function, which means we need the derivative of P. Then we'll set it equal to 0 and solve. Well, any questions or comments first before we jump into that derivative? Okay, it's a tough looking derivative only because the variables are slightly unusual. You can think of P as being, say, Y. You could think of I as being, say, an X, and that's an analogous way to think about it. But it's a good skill to just keep it into the same variables that it's presented in. If we mix up Y's and X's in that function, we might lose track for what we're even solving for. This is a very explicit question. solving for I. So let's keep it in this format and compute the derivative. In Leibniz notation, we're computing the rate of change of P, photosynthesis, with respect to I, the light intensity. So dP di, you could call it P prime if you prefer. It's also a quotient rule. So this is a good quotient rule review. We have to take the derivative of the numerator, 100i, multiply it by the denominator, I squared plus I plus 4, then subtract, copy the numerator, 100i, multiply it by the derivative of the denominator, I squared plus I plus 4, prime, then divide the whole thing by denominator squared. I squared plus I plus 4 to power 2. Okay, so there's the whole thing with the quotient rule. And again, the derivatives look tricky because we're not used to seeing our standard variables. But think of I playing the same exact role as x. It's the independent variable. So that's like x power 1. If you differentiate 100 times I, you just get 100 out. Maybe I should go on the next slide. I don't think I'm going to be able to squeeze that in. So we're going to get from the derivative here just 100. Multiplies I squared plus I plus 4. Copying all the way down to here, minus 100i. Then we multiply by this derivative. It's a degree 2 polynomial in the variable I. So on this term, we get 2 times I, following the power rule. When we differentiate a variable, like if we're differentiating x, we'll just get a 1. Here, if the variable is I instead, we still get a 1. So here's the 1, and the constant goes to 0 as normal. So that's our function so far. Divide by I squared plus I plus 4 to power 2. And if we stayed right here, say on exam 2 computing a derivative, I gave full credit for that because that's all the calculus. But in the context of optimization, that is not all the calculus. We need to find the critical number. So we need to solve an equation, this set to 0. And in solving that equation, we want this simplified as much as possible. So the algebra is just mixed in with the calculus now. We can't avoid that. To simplify this, we'll distribute 100 into this group to get 100i squared plus 100i plus 400. Do the same with this one. Distribute to negative 100i will give us negative 200 I squared minus 100i over, it's kind of tedious to copy this, but it's important, over I squared plus I plus 4 power 2. Then let me restate, this is still dP di. Simplifying from this line, we've got like terms, so that's always kind of nice. 100i and negative 100i cancel. These two to combine, and so we can write this out as 400 minus 100i squared. Divide by I squared plus I plus 4. We're nearly there. So once we get to this stage, we can do more work on this. We can factor out a greatest common factor of 100. Then it becomes a nice difference of squares, and we'll factor that further. I guess it's still a difference of squares, even in this form, but I think it's easier to work with if we factor first. So let's take out 100, leaving behind 4 minus I squared over I squared plus I plus 4. I forgot power 2 here on that first fraction. Let me copy it into the next fraction on the right. Last thing is to factor. So we've got 100. And difference of squares seems to come up a lot. I think this is the third time this week it's came up. This is something squared, 2 minus something else squared, I. So we can factor as 2 plus I times 2 minus I. All over that I squared plus I plus 4 power 2. We still don't have the critical number, but we're basically there at this stage. When we set this equal to 0, it's only the numerator which will affect the outcome to this. So setting that to 0 then implies 100, 2 plus I, 2 minus I equals 0. So same concept as we've seen in the prior sections. The only way a fraction actually evaluates to 0 is if the numerator itself was what went to 0. But the numerator is fully factored, so the only way this is 0 is if the first factor is 0, it's 100, so that's impossible. We move over to the second factor. This becomes 0 when I is -2. So I is -2, or the other possibility for getting 0 is if it came from that factor. Here I would have to be a +2. So, or I equals +2. So now we're not in the great spot, right? We did a lot of calculus, we did a lot of simplifying, but if we're using the first derivative test for absolute extreme values, there's an implied assumption here. There's got to be exactly one critical number, and yet we've got two. So this is a problem so far. Anyone see what the resolution is to this bit of a conundrum? Oh, trying to get everything on screen. It's kind of touchy sometimes. So the issue with this one is, again, we didn't do anything wrong with the calculus or algebra side. We got down to algebraically and calculus-wise, legitimate solutions, two different critical numbers. However, it's the context that changes things. The context is majorly important that I was light intensity, 0 being absolute darkness, and in this context, domain is 0 to infinity for I, it cannot be negative. That means at -2, that's just a nonsensical solution. It doesn't actually factor into the context whatsoever. If they tried to run this experiment with negative light intensity, we're not sure what that would even mean. Exactly. So because of the context, like Haley said, there is exactly one critical number. It's this one at 2. So let's put a kind of a light X on this. We're not saying we did anything wrong, that there's anything wrong with -2, but in this context, let's say it here just to make it clear. In this context, thinking of the domain of this original function here, I equals 2 is the unique critical number of our photosynthesis rate function. It was just named P. That means we're back in business. We can, in fact, use the first derivative test. Could we use a second derivative test? Maybe, but you need to differentiate that again. It's another quotient rule, and they get sometimes more complicated each new derivative you take. And it gets worse. Even after you do the second derivative test, you're going to have to use the domain condition here to argue this inequality. And that alone can be a deal breaker. Even after you did all the work, you might find that showing and proving the inequality is negative for all x is just way more work than anything you would have done in the first derivative test. So for these kind of problems, if it was a battle to get to here, for example, that's a good giveaway. The first derivative test is not just a good idea, it's probably the one and only way to get through it in any reasonable amount of time. And speaking of reasonable amount of time, I want to go carefully with this first derivative test. We've done it once in 4.2 when we had context. I don't want to rush through it in the 5 minutes and some change that we have left with time. So what we'll do is we'll come back to this problem after taking a well-deserved spring break. We'll be on the 31st, right before April Fools. And we'll show how the first derivative test goes now that we found the critical number. So this will be our stopping point for today. Any last questions or thoughts, folks, before we call it a day a bit early? Okay, well, when we come back, we'll run through this one carefully so we're not rushing through it in our 5 minutes we have. Then we'll do another kind of challenging problem where we have to build our own function. This is one's kind of similar to example one. But here, the idea is we'll use either the first derivative test or the second derivative test. This is how the exam questions are going to be written. It'll be up to you to decide which one makes the most sense. So in example 3 and example 4, the major ideas are as well explaining why we chose which test. We're going to pick the path of least resistance and find the test that works the best for these last contexts. But this will be our stopping point for today. Again, appreciate your all hard work. It's not easy to come to the last day right before spring break, but you all made it. I appreciate your work ethic. Have a great weekend or great spring break as well. And again, if you have any questions, I'm still available by email, so don't hesitate to reach out. I'll be checking in it each morning. But take care, folks. We'll see you all next couple weeks. Thanks. Have a good one.